Hi everybody, Physics Ninja here. Welcome to my video on energy problem review session. What we're going to do today is we're going to solve 16 problems. In total, there are 46 questions ranging from all types of problems involving conservation of energy. We're going to apply the work energy theorem to solve some of these problems. There are going to be some conceptual questions in addition to many of them that involve some numerical calculations. The problems involve all kinds of things. You're going to see springs in these problems, so you're looking at spring potential energy. We're looking at objects moving, so that involves kinetic energy, and objects could be, for example, going down a hill, so we were looking at the change of gravitational potential energy. So here's what you do. The first step you do is you download the problem set. So you go in the video description down below and click on the link, the work energy review problems. Download that, open it up, and now read the problems. Try out the problems by yourself first. Okay, that is the key to all of this. If you get stuck, that's okay. You can come watch the video solution after you've tried the problems. All right, so like with all my videos, if you like it, give it a thumbs up. Consider subscribing to Physics Ninja. It's the best way to support what I do. All right, let's get started. All right, here's our first problem. We have identical blocks start from rest at the same height above the floor on two different ramps. The first ramp makes a smaller angle with respect to the horizontal than the second ramp. So you're comparing those two angles here. The speed of the blocks when they reach the floor is V1 and V2 respectively. All right, first problem says, assume that both ramps are frictionless. Which statement is most correct concerning the relative speeds of the blocks at the bottom of the ramp? So in order to do this, what I'm going to call this is the initial point and this is the final point right here. And for this, we're going to use conservation of energy. So for both cases, you look at the total energy at the initial point and you set it equal to the total energy here at the final point. So let's have a look here. This is K final plus U final. This is the total mechanical energy. Now, if I start from rest, guess what? It means that my initial kinetic energy is 0 for both. And at the end, the other thing I'm going to do is I'm going to set the final gravitational potential energy here to be 0 on the ground. So what are we left with? Which one's going to be moving the fastest? It's whichever one has the bigger kinetic energy. Well, how do you calculate the initial gravitational potential energy? Gravitational potential energy is simply mgh. And since h is the same for both blocks, guess what? Both of those are going to have the same speed in this case if it is frictionless, and that is one of the keys. All right, so choice C is the best answer for this question. Question 2 says, now assume instead in both cases there is the same coefficient of kinetic friction between the blocks and the ramp. Which statement is now the most correct concerning the relative speeds of the blocks at the bottom of the ramp? So what would you say? Well, again, if you were just simply looking at this from a geometrical standpoint of view, you would see that here, this distance here would have to be longer if they start from the same height right here, right? That's simply from the geometry. The other thing that you would know is that the normal force for a block on a slope you can write as mg cosine of the angle theta. So the normal force is actually bigger in this case because the angle theta is small, okay? And cos of theta gets bigger as you make the angle smaller. So when you want to include friction, you would have to consider the work done by the force of friction. And in that case, it's what? Well, it's the force of friction, Fk, multiplied by the distance that you're going to displace, which is going to be delta x, and multiplied by cos of the angle now between the friction and the displacement. For both of those blocks, the displacement is down the ramp, and guess what? That force of kinetic friction is like this. So the angle that goes into my work equation is 180. Now, the other thing that's important that we said is the normal force is bigger, which makes what? Makes this kinetic friction bigger for block number 1 over here. And also the distance is going to be bigger. So that means that the work done by friction is going to be bigger over here for block number 1, the block on the left, versus block number 2. If there is more work done by friction, it means friction has a bigger effect on the speed. So we're going to conclude here that V2 is going to be bigger than V1 because V1 here simply has more friction. All right, great. The next problem says the block starts at a height now of 1.6 meters. The second ramp is inclined at an angle theta 2, which is equal to 55 degrees. And the coefficient of kinetic friction now is 0.65. You want to know what is the speed of the block at the bottom of the ramp. So for that, we're going to use conservation of energy in order to solve this problem. So we're typically using the first equation right here, except we need to add the work done by the force of friction. So let me just go ahead and write it all. So we're going to have my initial kinetic energy plus my initial potential energy plus whatever work was done by friction. And this represents the energy lost in that system. This here must be equal to K final plus U final. Now many of these terms are going to be equal to 0. U final is 0 on the ground. The initial kinetic energy is 0. And now all we have to do is we have to solve for the speed. Well, that speed appears right here in this final kinetic energy because this is simply 1/2 mv final squared. All right, what is my initial gravitational potential energy? It's mgh. And now the work done by friction, I'm going to go back to this expression right here. So let's work on this. Cos of 180 is -1. So I have the work of kinetic friction as being minus Fk multiplied by that distance delta x. So I guess the only other thing I need to know is what is this distance over here, delta x, for this ramp? Okay, this distance here is going to be, again, I can use some trigonometry right here. Delta x here is simply going to be h divided by sine of the angle theta 2. All right, so what you have to do now is simply substitute that over here into the work done by the force of friction. Again, what is that force of friction? It's the coefficient of kinetic friction multiplied by the normal. And the normal for a block on a slope is mg cosine of the angle theta 2. All right, so we have a lot of terms here to substitute in this work done by friction, but let's keep going one step further. So this is what you get. You get minus mu k. The next term is the normal force, mg cosine of theta 2. And now the next term I'm going to substitute is that delta x, that displacement along the ramp, which is simply h divided by sine of theta 2. All right, you can combine that cosine and the sine to have a tangent here in the denominator. But now let's just go ahead and maybe substitute this whole term right here. So it's minus mu k, mg, and then h divided by tangent of theta 2. Now we're going to simplify some of the terms. You notice that the mass is everywhere, so you can go ahead and eliminate the mass. The other thing now is I can simply just isolate for v final. So this is what I'm going to do right here. So bring the 2 on the other side, and I have to take the square root. So this is what my algebra looks like for my final expression. All right, I get 2gh, 1 minus mu k, and then here I have to simply divide by tangent of that angle theta 2. All right, so now we substitute our numbers in here. We get 2, 9.8. The height was 1.6 meters. 1 minus that coefficient of kinetic friction, 0.65. And now divided by that tangent of 55 degrees. All right, be careful when you enter all of this in the calculator, but if I did this correctly, I should get an answer of roughly 4.14 meters per second. All right, and that corresponds to choice D, I think, is the best answer for this problem. All right, kind of a nice problem here involving not only mechanical energy, but also including the effects due to kinetic friction in this problem. All right, here's problem 2. We have a block of mass MA, 3 kilograms, slides on a frictionless inclined plane. It's connected to a hanging block of mass MB by a massless string that runs over this ideal pulley over here. The incline makes an angle of 30 degrees with respect to the horizontal, and the acceleration of block A is 1.9 meters per second. All right, going up the incline. So the first question says, as block A moves a distance of 1.5 meters up that incline, what is the work done by the tension in the string? All right, so this is what we first do. Let's do a free body diagram. So that's the block MA. I write the forces. You have MAG acting down. What else? I have a tension force acting along that string. And I also have a normal force. It is frictionless, so that's it. That's all we have for that. Now what they're looking for here is simply the work done on A by that tension force. Again, that is a constant force, so we simply apply our equation. It's the magnitude of the force, which is T. It's the magnitude of the displacement, which is delta x. Delta x is how far you move up this ramp. And then multiplied by cos of the angle between that displacement and that force. Well, guess what? The force is going up the ramp, and the displacement is also going up the ramp. So that angle here between both of those vectors is 0 degrees. So we don't have to worry about that. Cos of 0 is simply 1. So now we have to figure out, what is this tension force? Well, in order to figure out the tension, what we're going to do here is we're going to look at our free body diagram. I'm going to choose this to be the positive x direction. And I'm going to choose that vertical to be kind of perpendicular to that ramp. And now what I'm going to do is I'm going to apply Newton's second law, which says I have to add all the forces here. And I'm going to do that in the x direction. In this case, there are two. There's the tension acting up the ramp, and there's a component of the weight which is acting down the ramp. So that is actually MAG sine of the angle theta. And that's the angle theta from the ramp here. This is the angle theta from the ramp. Let me call it theta r so there's no confusion over here. All right, that's it. These are the two forces in this x direction. And now I have to set that equal to the mass of that block multiplied by the acceleration. What this allows me to do is it allows me to solve for what the tension is, because you simply bring this term on the other side and you can factor out the mass ma, and you're left with this plus g sine of theta of that ramp. All right, the last step now is you simply substitute that tension here into my work equation, and we substitute in all the values. All right, so what we're going to do here, this is ma, the acceleration of the blocks, g sine of theta of the ramp, and multiplied by that displacement. I don't need this last term anymore. This is simply equal to 1. All right, now we substitute. So what is my mass ma? It's 3 kilograms. That acceleration is 1.9. Little g, 9.8. Sine of 30 degrees. And now my displacement, they said, was 1.5 meters. All right, that is the work done by this tension. So you go ahead and you substitute all those numbers in the calculator, and I think I got an answer that was roughly 30.6 joules. Okay, and that there corresponds to choice B is the closest. Let me go ahead and box that up. All right, question. The next question says, as block A moves a distance 1.5 meters up the incline, how does the magnitude of the work done on it by the tension in the string compare with the magnitude of the work done by gravity? Okay, so what do we think about this one? Well, which one does the most amount of work? Okay, well, let's think about it. Are those forces the same? We know actually that the tension here is bigger than this component of the weight, right? It's bigger than MAG sine of theta A. Now we know that, what else? The perpendicular component of this weight doesn't do any work. So we're only really comparing the work done by the tension to the work done by this force right here. And guess what? The work done by the tension is going to have to be bigger, okay? Because it is accelerating up. So C here is the best answer. All right, look at the next problem. The next problem says, as block A moves a distance 1.5 up the incline, what is the total work, okay, done on both blocks by the tension in the string? So we've just calculated how much work was done on block A. Let's think about how we would do the work done on block B. How would we do that? Well, you do a free body diagram. You do mg, and that's mbg acting down. We'd have our tension acting up. And now what else? I would have my displacement, delta x, acting down. So what would be the work done by the tension here in this case? The work done by the tension on block B would be the magnitude of the tension, the same tension we found previously, the magnitude of the displacement, and what is the angle now between the tension force and my displacement? In that case, it is 180 degrees. So here I'm going to get cos of 180 degrees. That's in the work definition. So this guy right here equals to -1. And guess what we're going to get? The exact same number in magnitude, but it's going to have a negative sign in the front. So if you look at this expression here, the work done by the tension on block B is simply minus T multiplied by delta X. Well, for block number A, we simply had T multiplied by delta X. So if you add up the work done by each case, right, you're going to get 0, okay? So the total work done by the tension is actually 0 in this case. Kind of a little bit of a tricky problem, but this is one way that you could get to the solution. All right, let's look at problem 3 now. All right, here's problem 3. We have a graph over here. It says a one-dimensional force f of x shown in the graph acts on a particle that is initially at rest at x equals to 0. First problem says, what is the work done by the force on the particle as it moves from x equals to 0 to x equals to 5? All right, one thing to remember is if you're given a force versus position graph, the way that you calculate the work is simply equal to the area under the curve. And in this case, we're worried from x equals to 0, which is right here, all the way to x equals 5. Now, first we note that in some points, you see that this area here is positive, and in other cases, it's negative. So let's just kind of simplify this a little bit. I would break this down into rectangles and triangles. So we could see right here that both of those are going to have equal and opposite areas, so those things cancel out right here. The other thing to notice is that this triangle right here has an area, but it's exactly going to be half of whatever this guy is. So at the end, the total area under the curve is the area of one of those triangles, right? It's really half of this square. So what we get here is 1/2. The base is going to be 1, and the height is simply going to be 2. Therefore, we're going to get 1 joule of work done from x equals to 0 to x equals to 5. So I think B is the best choice. All right, the next problem says, which of the following best describes the motion of the particle as it moves from x equals to 1 to x equals to 2 meters? So let me clean this up a little bit. So we're looking from this position to this position. Well, know what we have over here is we still have a force. Now, the force is getting smaller, but the force is what? The force is a positive value, okay? And the particle is moving in that positive x direction. So if the force is positive, guess what? It means that there's going to be an acceleration is also positive. So that means that it has to be speeding up. So you can get rid of anything here that says slowing down. It's not slowing down. It's also not moving at constant speed because there's a force acting on it. All right, what else? What direction is it moving in? Well, it really has to be moving in the positive x direction. It hasn't stopped moving in the positive x direction here from 0 all the way to 2 seconds, even a little bit beyond that actually. So right here is it has to be speeding up. E is really the best choice. All right, the next thing, problem says, compare the speed of the particle at x equals to 1 to the speed of the particle at x equals to 3. So let's clean this up again, and let's look at the 2 points that we are comparing. All right, we're comparing at x equals to 1, which is right here, and all the way to x equals to 3 right here. All right, so what do we have? Well, for this, what we're going to do here is I'm going to apply the work energy theorem. So imagine you were right here, and you're going to be moving here at some speed v. Now, let's calculate the total work under the area under the curve from going from 1 all the way to 3 seconds. You could see again that you're simply looking at the area of this triangle and the area of this triangle. Here you're going to get a positive area, and here you're going to get an equal and opposite negative area. So how much work is actually done from going from 1 to 3? Again, that represents the total area, and that represents 0. So what does that mean? It means that if you apply now the work energy theorem, the work energy theorem says you look at the work done in any period, it's equal to the change of kinetic energy in that, comparing those two positions right here. So what does that mean? Well, it means that the kinetic energy at point x equals to 1 is equal to the kinetic energy at point equals to 3, because this is k3 minus k at 1 meter. Therefore, if the kinetic energy is the same, it means that the speed is the same. So really the best choice for this one here is choice B, because it says the speed is going to be the same, because there is no net work being done. Sure, the particle here might speed up in this time interval from 1 to 2, it speeds up. But then what happens? We switch the force direction. So here it slows down. So whatever speed you gain going from 1 to 2, you're going to lose when you go from 2 to 3. All right, that's it for this problem. Let's go to the next one. All right, here's problem 4. We have a box of mass m initially at rest at x equals to 0 on a horizontal frictionless surface. It's attached to an unstretched spring with a spring constant k, aligned with the x-axis, whose other end is attached to the wall as shown. All right, a hand applies a force to the box in the positive x direction, so it moves to the right with a constant velocity until it reaches x equals to d, and then it stops moving. All right, our first question says, what is the work done by the hand on the box? Well, let's think about this. Let's do our free body diagram. We've got the weight. We've got a normal force. All right, we've got the force of the hand, which is this way, FH, and guess what else? We're going to have a spring force, which is going to be the other way, which is opposite of the compression, right? All right, so how would you actually do this? Well, first of all, let's determine whether or not the work should be positive or negative. So we have the force of the hand, which is pointing to the right. And then what else? We also have a displacement, which is also going to be in this direction over here. So since the force and the displacement are parallel to each other, we know that the work done by this force of the hand has to be a positive value. It has to be greater than 0. So it's not going to be equal to 0. This first choice here, if I integrate this, I'm going to get a negative value. So that can't be it. All right, so now you're left with a bunch of choices. This bottom one here is also going to be negative. So how do we determine whether it's choice C or choice D? Well, have a look at the expression here that you're integrating. Remember what you're integrating here and think about the force of the spring. The force of the spring, you should know, is minus kx. Okay, so if I was looking for the work done by this force of the spring, well, what I would do is I would integrate that force of the spring and I would integrate that over the distance. In that case here, I would have the answer B, which is minus, right? Minus integral of kx dx, going from 0 all the way to d. But this here's the work done by the force of the spring, which is going to be negative because that force is to the left and the displacement is to the right. The other thing to note is that it starts from rest and then it moves at constant velocity and then it stops moving. So the net work being done, right, the total work or the net work being done is the change of kinetic energy, which has to be 0 in this motion. So whatever you have, the work done by the spring force plus the work done by this applied force, they must sum to 0. So this one here is negative, and this one here is simply going to be the opposite sign of that. So the correct answer here really has to be choice C. And also this one over here wouldn't really even have the right units if you integrated that, right? If I integrated an x squared dx, I would end up with an x cubed function, and then I multiply that by some spring constant. This here has the wrong dimensions, all right? This is not measured in joules, okay? Because it's kx cube. All right, so I think that's good enough for that one. Let's go to the next one. Suppose your answer to the above question is work WD, okay? If the hand instead pushes the box twice the distance, the work done by the hand on the box is the work with a 2D here in the subscript. How does the work compare one versus the other? All right, well, if we think about this for a minute, again, if this is moving at constant velocity, it means that my force of the hand is actually equal to the force of the spring. So if you go from 0 to d, the force of the hand is linear with that distance x if you plot the force of the hand. If I continue that now all the way to 2d, this is what it looks like. Now, if I'm looking for the work, what do you think I am trying to do over here? The work represents the area under the curve. So what do we think it is? Again, that area under the curve is going to be bigger than the area going from 0 all the way to d, right? That is the work done WD. This guy over here is the work done if I push it twice the distance, right? Twice the distance would be actually the total area over here, from going from 0 all the way to 2d. But you see in this case that the work WD has to be bigger than twice the value of D because of just that area. Here you're looking at the area of a triangle. Here you're looking at a much bigger triangle, but that area is more than twice the size. All right, so in this case, I think the best answer here would be choice C. By looking at a graph of force versus distance is kind of an easy way to answer that. What is the total work done on the box by all the forces? Well, this one we've kind of already answered. Because you're moving at constant velocity, we know that the net work equals to the change of kinetic energy. This right here is what you call the work energy theorem. Since there is no change in kinetic energy because I started at rest and I finished at rest, it means that the total work here must be 0. Okay, kind of a nice problem for work energy involving springs. All right, here's problem 5. We have a ski slope. Try that again. A ski slope starts at point A, descends to point B, climbs back up to point C, then goes back down to D. To the right of point D, the surface is level right over here, and the coefficient of kinetic friction between the ground and the skier is mu k, as indicated in the figure right here. What else? There's no friction anywhere to the left of point D. So this whole part with the undulations, no friction. The elevations of all these points here, B, C, and D, are given over here. That's 30, 90, and 0 down at the bottom. The skier starts from rest at point A and then slides down the hill. Now she is observed to move at 18 meters per second over here. So we know right here she has some kinetic energy. All right, the first question is, what is the starting elevation over here at this point? So we're basically looking for what is the height here of point A. So what I would do here is, since there is no friction here between A, B, and C, let's use all the information, for example, between point A and C, and say that the total energy must be conserved since there is no friction. So my total energy now is going to be, well, at point A, the only thing I have is gravitational potential energy because I start at rest. That must be equal to the total energy at point C. Well, at point C, I know I have some kinetic energy. And guess what? I'm also off the ground. So I have to actually put the height here of point C in there. So what else? Now I'm trying to find what is the height YA. So what I'm going to do is just divide through by mg. So I can cancel out right over here. I can cancel out the mass, but now I have to also divide by little g. And now the only thing we're left here is just to substitute our numbers. So we get 1/2. This here is 18 squared. 9.8, and again plus that height at point C. That height at point C is 90. So if I put that in a calculator, I think I get 106.5 meters, and that corresponds to choice C being the best one. All right, question 7 says, if the skier slides a distance of 440 meters beyond point D before coming to rest, what is the coefficient of kinetic friction? So guess what? Well, we know that down over here we have K final equals to 0. Now we know that the total energy, we know what it is because it's simply all of the energy at either point A, C, or point D. Doesn't matter which point you consider, the total energy is the same everywhere. And guess what? We're going to lose all of that energy to energy loss due to friction. Now the energy loss due to friction is simply calculating what is the work done by the force of friction over that distance. Well, it's the coefficient of kinetic friction times the normal force. That is the force of friction. The distance that I'm sliding now is going to be that distance of 440, which I'm calling delta x. And now I'm just going to write the work done by the force of friction. I put my cos of 180 in there because guess what? As this object is sliding, right, she has a force of friction acting on her, Fk, and there is a displacement going in this direction. The angle between both of those is 180. So my work done by the force of friction ends up being a negative number, mu k mg delta x. All right, now how much energy do I have when I started? Well, again, all that energy is going to be gravitational potential energy. And my final is going to be 0. So at the end, all we have to do here is just set this equal to the minus that initial energy that I start with, because I'm going to lose all of this energy to work done by that force of friction. So this is mg delta x. At the end here, we can cancel out the mg's. There appears on both sides. We also have those negative values that also appear. So what we're left here is that Oh, it's not the distance that I'm trying to solve. I'm sorry for that. We're looking for that coefficient of kinetic friction, mu k. All you have to do here is put that height that we just calculated and divide that by that total distance that I slid. So here this would look like simply 106.5 and divided by 440, that distance that I slid before I came to a stop. That gives me a coefficient of kinetic friction of roughly 0.24. That corresponds there to roughly choice A. I think is maybe the best choice for this. Again, there are many ways to kind of attack this problem here. I'm kind of just doing it just by looking at how much energy I'm going to lose in this process. I'm going to lose all of my gravitational potential energy, and I lose that to work done by friction. All right, let's look at the next one now. It says if YA and mu K are kept the same as above, but the elevation of point C is reduced by 15 meters. The distance beyond point D that the skier would slide before stopping would be what? All right, so let's see what we change and what we keep the same. So imagine here I reduce this elevation here of point C by a little bit. Well, guess what? This is still frictionless right here. So it doesn't change how much energy you have at point A. It doesn't change how much energy you're going to have at the new point C or that energy that you have at point D because you're not losing any energy due to friction. So at the end, the amount that you're going to slide, if you look at the distance that you're going to slide, the distance that you slide actually only depends on what was that initial height and what is that coefficient of friction. And that there is simply not going to change. Therefore, the distance is actually still going to be equal to 440. All right, here's problem 6. We have a bobsled here, has a mass of 210 kgs initially at rest at point A. I'll just highlight that. At the top of the track is shown in the figure. The distance from A to B right here is 15 meters and is horizontal. From point B to point C, the track is twisted and turns as it moves down the hill. That vertical distance from point B to point C, that height right here is 70 meters. The track is not frictionless. All right, question 19 says we have 4 men, each having a mass of little m, 85 kg. Start pushing the sled from point A toward point B. Each one pushes with the same force as 65.6 newtons over that entire distance. When the bobsled reaches point B, its speed is 5 meters per second. What was the total work done by the forces on the bobsled from A to B? All right, well, for that, what I would do is I would use the work energy theorem, which says that the net work being done on the sled is simply equal to the change of kinetic energy of that sled, right? So that's it. This is always a final value minus an initial value. And keep in mind that initial value is 0 because you started from rest. So all we need now is that final kinetic energy, which is 1/2. It is big M here. Let me be a little bit careful here. This should be big M, the mass of the sled, and V squared. 1/2 multiplied by 210, and that speed at the end was 5 meters. And don't forget to square that. I put those numbers in the calculator. I get 2,625 joules of work was done by that force. So that is choice C right here is the best one. All right, question 20 now. It says the 4 men jump on the sled at point B and slide down. As they pass point C at the bottom of the sled, their speed is now increased to 25 meters per second. What was the work done on the bobsled and the men by non-conservative forces? Okay, so non-conservative forces as they move from here all the way to the bottom. So when they ask you for work done by non-conservative forces, the word that should pop into your mind is they want to know the work done by friction. Okay, so one thing we're going to do here is we're also going to use the work energy theorem. So again, we already have the work energy theorem right here. We are just going to look at this left-hand side. What is doing work? Well, there's going to be work done by non-conservative forces or by friction. I'll just call it non-conservative here, NC. What else? There's also gravity acting. There's going to be the work done by gravity as you go from B to point C. And guess what? That is it. So that must equal to the change of kinetic energy. And again, now our initial and our final point are B and C points. So now all we have to do is simply rearrange this, bring the work done by gravity onto the other side, and it looks something like this. we have delta K, and then whatever plus, oh, I'm sorry, that should be minus if I bring it on the other side, minus the work done by gravity. Okay, at this point we can start substituting in other equations. So what is the change of kinetic energy? Well, it's the final kinetic energy, that's the velocity at point C, minus 1/2 m velocity at point B. And how do you calculate this work done by gravity? All right, the work done by gravity here, there's many ways to do it, but the work done by gravity, you can write it as minus the change of potential energy. This is minus U final minus U initial. So what you can do here is just multiply that negative sign through, and what you end up getting is the initial potential energy minus the final potential energy. So this is one easy way of calculating the work done by gravity in this case. And for us, the final potential energy is 0. So all you have here is U initial. So I go back over here and I have to do minus U initial over here. All right, so we're in a position now where we can start substituting in all the numbers. One thing you have to keep in mind is what is this mass here that appears here? It's also going to appear in my initial potential energy because potential energy here is simply going to be mg multiplied by that height. But think about what we have here is we have not only the sled, but you'll also have the 4 men that are inside the sled. So my mass really should be 4 times the mass of each one of 85. Again, plus the big mass of the sled, which is 210. So this here is actually the total mass that we should be substituting inside our equation right here. If I do that calculation, I think I got 550 kg. So that is the mass we should be using right here. So to clean up the math here, what I end up doing here, I'm just going to factor out the 1/2 m in the front. And now what am I left with? I'm left with that speed at point C. I'm left with the speed at point B, which is 5 squared. And now this last term, be a little bit careful here. I'm going to get minus 2 because I factored out a 1/2 here of all the terms. Little g is 9.8. And that height here for that initial potential energy was 70 meters. All right, so you put everything in the calculator. Again, the work done by non-conservative forces is going to be a negative value. And what I get here is roughly minus 212,000 joules. All right, let me box that up. And that there corresponds to roughly choice A, I think is the best choice for this problem. All right, what's next? What is the total work done on the bobsled by all forces between point A and between point C? Well, at A, we started from rest, and at point C, we're moving at 25 meters per second. So there's been a huge change of kinetic energy, right? So what would we expect? The work energy theorem says what? If there's a change in kinetic energy of the system, what should we get? We get positive work that is done over on this side. So that one's pretty straightforward, I think. Choice B is the best answer. All right, here's problem 7. It says a student is pushing a box of mass 50 kg across a level floor at constant speed of 1.5 meters per second. The student pushes on the box with a downward force of 160 newtons at an angle of 31 degrees below the horizontal. The box moves a distance of 14 meters across the floor. They tell you there is friction here. There's a coefficient of friction between the box and the floor, and that value is mu k. We are not told that value, however. Question 6 says the total force done by all forces on the box as it moves a distance d across the floor. Is it positive, is it negative, or is it 0? So this is a direct application of, guess what? Our work energy theorem. So all you have to say is that the total work or the net work is the change of kinetic energy. But what is the change of kinetic energy if the speed is constant? Right? That means you have K final minus K initial of the box. And those things are the exact same because the speed is constant. So that means we have to have 0 net work being done by all of the forces. All right, not bad. What about the next one? Question 7 says, what is the work done on the box by friction as it moves a distance d across the floor? Well, the thing I would do, they're asking me for the work done by friction. I would just do the work done by F like this. It is the force of friction, Fk, what else? Multiplied by the distance d and multiplied by cosine of 180 degrees. That's what I would do. Let's think about this. So what do we have? We've got our free body diagram here. You remember, you got friction acting opposite of the motion. That's kinetic friction. And I have a displacement, which is D in this direction. The angle between that D and that force of friction is 180. Now, one problem with this method here, as you're going to find out, is if you try to write this force of kinetic friction, you write it as mu k multiplied by the normal force, which in this case is big mg. That's it. But we don't know what this is, right? We don't know what mu k is. Therefore, it's a little bit difficult to calculate it using this equation. So another way we could go about this is to use the work energy theorem. Again, we're just going to use this side over here. We know it moves at constant speed, therefore this whole term for the work energy theorem is 0. So it says that the net work is equal to 0. Well, what is doing work in this problem? Think about it. There is this applied force that is doing work. I'll just call it work done by F. There's also the force of friction, which is acting on the object, so I'll call it WF. And again, that is it. There is gravity acting down and there's the normal acting up. Those forces don't do work in this problem, so that's it. We have to sum both of these and get to 0. So the work done by friction, you see it right here on the left-hand side. The work done by friction has to be minus the work done by this pushing force. So this is how you can calculate it because we know the value of the pushing force. So let's think about what we have. Now we're going to apply our formula for work done by a constant force. So it's the magnitude of the force F, which we know, the distance that it slides, and now cos of the angle, it's actually going to be cos of this angle theta right here. Now we could substitute in all our numbers. So the work done by friction, notice it's going to be negative. This force is 160. That distance that it slides is 14 meters, and here it's cos of 31 degrees. We put all those numbers in the calculator, punch things up, I get minus 1920 joules. Let me box that up. That should correspond to one of the choices, and there it is. Choice E is the same value we got. All right, question 8 says the work done by the box on the student during this motion is what? The work done by the box on the student, well, let's think about how we calculate this. If the student pushes on the crate with a force F, it means that the box pushes on the student here with a force F, but in the opposite direction, right? It should be something like this. This is the force of the box on the student. All right, and guess what? That angle there is also going to be what? It's going to be 31 degrees, the same as it was. Now the displacement is what? It's in this direction right here. That is my distance D. So how do we go ahead and calculate the work done? Well, right away you should see that if I have a force that has a component at least, remember this force I can break it down into two components. And this component here is the box on the student, again multiplied by cosine of 31 degrees. You can see that this force and that displacement, they are 180 degrees apart. Whenever you have that, you're going to have negative work being done by that force. So this one's a little bit tricky, right? Because they're asking by the box on the student. You need to evaluate what this force is. Again, we're only looking for the sign right here, so this should be a negative answer. A little bit of a tricky problem. All right, let's look at problem 8 now. All right, here's problem 8. It says a 21 kilogram dog is initially at rest. When he sees a squirrel at time equals to 0, he starts running toward the squirrel. At time equals to 1.5 seconds, the velocity of the dog is 4.1. An elastic band that connects the dog to a stationary post starts to stretch and eventually stops the dog at a time of 1.8 seconds. Question 9 says, what is the magnitude of the average force exerted on the dog between time 1 and time 2? All right, so in order to solve this one, what I would suggest doing here is, actually this one's not really a work energy type of problem. The best way of solving this one is to use the impulse momentum theorem, which says this, that the average force multiplied by delta t, that's that impulse, has to be equal to the change of momentum of that dog, which is simply the mass times the change of velocity of that dog. So if we're looking for the average force, we just isolate here the average force. is m delta v over delta t. And this really is nothing more than Newton's second law, right? Because this term is the acceleration of the dog. So what is our mass? Our mass is going to be 21. What else? The change of velocity is v final minus v initial. Again, they're only looking for the magnitude here, so I wouldn't worry too much about the sign. So that delta v is simply going to be 4.1 meters per second. And what else? Now, what is that change in time? I'm looking between time 1 and time 2. That delta t should be 0.3 seconds. We put those numbers in the calculator. We get an average force of 287 newtons. All right, that should correspond to choice B right here is probably the best choice. All right, next one we said, what is, again, the magnitude of the total work done on the dog between these two times? Now, it says you have an elastic band that stretches, so you might be thinking of potential energy and change of potential energy. That's fine. But we don't know what the spring constant is, so it's a little bit hard to approach that problem this way. If we're looking for the total work, however, we also know we could use the work energy theorem, which says that the work done, or the total, or the net work, whichever one you want to call it, has to be equal to the change of kinetic energy. Guess what? This is K final minus K initial. K final in our problem is 0 because the dog stops right here at 1.8 seconds. All right, so now all we need to do really is calculate what is this initial kinetic energy of the dog. mvi squared. This becomes minus 1/2. The mass of the dog, 21 kg. That initial velocity is 4.1 squared. All right, so I get that the net work acting on the dog is minus 177 joules. Again, they're simply asking me for the magnitude of that value. So again, you could just drop that negative sign right here. And that is what you're looking for. Again, choice E is the correct answer for this problem. Let's look at problem 9 now. All right, here's problem 9. We have a block of mass, 3 kilograms, starts from rest and slides down a frictionless slope of a height of 2.1 meters. After traveling across a horizontal surface, okay, with this distance d, the block hits the horizontal spring with a spring constant given by this value. All right, question 20 says, if the horizontal plane is also frictionless, what is the maximal distance that the spring will be compressed? So in order to tackle this one, what I would say is I would look at this as the initial point, and at the maximum compression might be over here. This will be my final point. Let's use conservation of energy. There is no friction anywhere. So what we would say is that the energy at the initial point should be equal to the energy at the final configuration. What we have initially is all we have is gravitational potential energy, which is mgh in this case. At the end, what we're going to have here is that the spring has reached its maximum compression, which we're calling Dmax. And all of the energy gets stored into spring potential energy. And the amount of spring potential energy that you get is 1/2 K Dmax squared. All right, so what we want to do now is simply solve for Dmax. So all you have to do here is isolate and substitute. I'm going to get an expression here for Dmax. Just do the algebra. You bring the 2 on the other side. You get mgh, you divide through by that spring constant k, and then you have to square root everything. So now we're in a position where we could substitute all the numbers. So we get 2, the mass is 3 kg, little g is 9.8, and my height was 2.1 meters. Divide that now by, this is 2 times 10 to the 3, that is 2,000 newtons per meter. All right, put that in the calculator and I get a Dmax value, which was approximately equal to 2.49 meters. All right, go ahead and box that. That is the correct answer, and that corresponds to choice A for this problem. All right, question 21 says, if the mass of the block were doubled and the spring constant was halved, and the block was released from the same height, how would the new compression, now Dmax new, compare to that original one that we have in this first problem? Well, let's think about what we're going to do here. So we're going to call the new mass m prime, and m prime is simply equal to twice the original mass. We're also going to call the new spring constant k prime. We are halving that spring constant. So let's look at our new Dmax. So let me go ahead and write new like this. So what would that look like? Well,
Let's substitute our values. So we have 2. Here's the expression up above. The mass now is m prime, but I'm going to substitute that now for 2m. We still have little g. We still have the same height. And now we have to divide by the new spring constant, which is the original one divided by 2. So if you factor everything out, you're going to get an additional factor of 4 here under the square root. And once you take the square root of that additional 4, what you end up getting is 2 multiplied by this entire term, which is nothing more than what? That's the original D max value that we had. So what you end up getting is it's exactly twice the original D max value. That's a nice problem. All right, question 21 now says, now suppose there is friction when the block is sliding on this horizontal surface right here. So we have friction. And the same coefficient of friction is 0.15. If the mass and the starting height are the same as in the first question, what is the speed of the block? Again, it's just before hitting the speed, hitting that spring right here. So how would you find the speed of the block? Well, for that one, what I would do is I can use conservation of energy here. I would say that at the initial point, what I have is some gravitational potential energy. I have no kinetic initially. I'll just write it down as K, but again, that's going to be equal to 0. And again, at the end, that has to be equal to U final plus K final. Now, the thing that's missing here is we have to account for friction over here. So the way you account for friction here is here you have to add the work done by that force of friction. You could use the work energy theorem. It's going to end up looking exactly the same. Now my final gravitational potential energy, that is when you're over here down at the bottom. So what are you going to get for that? You're going to get 0 for that value. All right, and now, well, what we want to do now is we want to calculate what that final speed is. So in order to do that, the final speed is going to be inside this final kinetic energy. So let's go ahead and just work on this expression. What is my initial gravitational potential energy? It is mg multiplied by that height, plus how much work is done by friction. All right, we think about friction as that block here is sliding. So you have the weight acting down, we have the normal force acting up, and if it's sliding to the right, it's going to have a force of kinetic friction acting in that direction. That force of kinetic friction is that coefficient of kinetic friction, again, multiplied by the normal force. Let me just replace that over here. The normal force is simply equal to the weight in that case. So to calculate the work done by the friction, we take that magnitude of the force. We take the magnitude of the displacement multiplied by cos of which angle? Again, the displacement is to the right. The force of friction is to the left. The angle is 180 degrees between both of them. So that will give you -1. And that there must be equal to K final, which is 1/2 m v squared. And v is what you're trying to solve for. All right, one thing we noticed that can cancel out here, all these masses can cancel out. That simplifies our expression. I could bring the 2 on the other side and write one final expression for that speed. So this is what it looks like over here. I'm going to factor out the 2g, and that appears in both terms over here. And what I'm left with here is h minus, the minus comes from the cos of 180, the coefficient of kinetic friction multiplied by that distance. And now you could just substitute all the numbers. So you get 2, 9.8. That original height was 2.1 meters. The coefficient of kinetic friction, 0.15. And now that distance that you slide is 3.2 meters. All right, we put everything in the calculator, and you should get a speed here, v, of roughly 5.64 meters per second. Running out of space here. Let me go ahead and box that up. That gives you, which choice over here? We get 5.64. That's choice B. All right, great. So this is kind of a nice application of either work energy theorem or conservation of energy, but you need to include this work done by the friction to account for any energy loss here during that sliding portion. All right, here's problem 10. We have a mass M1 of 8 kilograms is being pulled up the ramp at constant speed by a rope that passes over a pulley that's tied to the top of a mass M2 over here of 12 kg. Initially, the distance between the bottom of the second mass on the ground is little d, which is 1.5 meters. The ramp's angle of inclination is theta, which is 25 degrees. And there's an unknown coefficient of friction between the block and the ramp right here. First question says, what is the total work done by gravity on both blocks when this guy drops a distance d2? Okay, so this is what they're asking for. You just write it down and say the work done by gravity on block number 1 plus the work done by gravity on block number 2. Notice that the work done by gravity on block number 1 is going to be less than 0, and the work done by gravity on block number 2 is going to be bigger than 0. How do I know that? Well, think about it. Here we have the force of gravity, m1g, and the displacement is going to be this height right here, right? So these are in opposite directions. Sure, it's going up the ramp, but again, this is one quick way of checking what the sign of the work should be. For block number 2, what do we have? We have m2g acting down, and we also have a displacement d, which is down. These are in the same direction, so this one would be positive work. All right, so how do you calculate the work? Well, for this one, I'm just going to say that the force is constant. So I'm just going to use this equation, the force, the displacement, and cos of the angle between both of those vectors. And I can use this whenever there's a constant force. So this is what we have for block number 1, right? So you have m1g, that's the force acting down. My displacement now is going to be a distance d and that way. Now the angle theta that goes into the equation is this angle here. So which angle is that? Well, if you think about that ramp makes an angle of 25 degrees, which means that this angle right here is actually 115 degrees. So this is how you write down the work done by the first one. So you say it is the magnitude of the force, m1g, the magnitude of the displacement, which is d, multiplied by cos of 115 for this one. And cos of 115 is going to be a negative number. So that's going to make this first term negative. Plus, what is the work done by gravity for block number 2? It's the force of gravity on block number 2, m2g. The displacement is d, multiplied by cosine of 0 degrees, because the force on block number 2 is acting down, m2g, and my displacement is also down, d, 1.5 meters. So there is 0 degrees. Those two vectors are parallel to each other. So at this point, you just substitute in the values. So you get 8, 9.8. That distance is 1.5. Cosine of 115. And plus m2 is 12. Little g again, 9.8. I could have factored that out to simplify this, but let's just keep going. And at the end, I'm going to get that the total work done by gravity, just call it WG now, the total, which is the sum of both of those terms, gives me 127 joules. All right, and that there corresponds to choice number C. All right, what about the next one? They say, what is the total work done by all forces, okay, on block number 1 as M2 drops the distance? So what we're looking for here is, what is the net work, the total work? For that, I'm going to apply the work energy theorem, which says it's the change of kinetic energy. Well, now we've got to go back to the problem statement. And there is this key word right here. Everything is moving at constant speed. Therefore, the change of kinetic energy is 0. So the net work done, that's a simple one. See if you're paying attention. The correct answer is A. That's it. That's all. All right, problem 19 says, now what is the tension in the rope? And we have 3 choices here that compare tension to the gravity, force of gravity acting on that second block. So I would start by writing this second block and doing a free body diagram on it. So this is what you have. You have the force of gravity acting down. And what else? Well, we have the tension acting up. Now, the other thing that we know is that V is a constant. So that means that the acceleration is 0 for that block, for both blocks actually. And the only way I can have that is if the tension is actually equal to the weight. So right away you should be able to write that choice B is the correct answer for that block. All right, here's problem 11. We have a block of mass, little m, 4 kilograms, is released from rest from the top of a frictionless incline. The initial height here is h. The block slides down the incline plane and then along a rough horizontal surface for a distance of 0.4 meters. Then It hits a spring. The spring has a has a spring constant of little k, 45 newtons per meter, and the spring compresses an additional distance here of 0.15 meters from equilibrium. This entire horizontal surface here has a coefficient of kinetic friction of 0.2. All right, the first problem says what is the height of the ramp? All right, for this one, I'm going to use the work energy theorem. And there's a few things. First of all, it's released from rest. And then what? It compresses a spring, right? And the maximum compression is D. So that means it starts from rest. And once it compresses this spring, and it's right here, the velocity is also 0. That initial velocity is 0, and the final velocity is 0. So guess what? It says that the total work, or the net work done on that block throughout this entire process has to be 0, because that is the change of kinetic energy of that block. So now we have to include all the terms here that are doing work. So we're going to have gravity that does work for the ramp section of it. We'll call that work done by gravity. What else? Once it hits the flat section over here, there is going to be work done by this force of kinetic friction. And then once it starts compressing that spring, there is also work done by the spring. And at the end, when you sum those three terms, they'd have to be equal to 0. So let's worry now about the conservative forces. The conservative forces are the gravity and the spring. For both of those, you can calculate the work done by any conservative forces as being minus the change of potential energy, which is U initial minus U final. Okay, that is a definition. So let's think about gravity. Gravity, you start here very high. The potential energy is mgh. So this is what you have. You have mgh for the work done by gravity during that case. Notice we get a positive number. The final gravitational potential energy here is 0 because you're going to be on the ground. What about now the work done by friction? Well, the work done by friction, again, imagine doing a free body diagram here. What you're going to have is that the force of kinetic friction is this way. What else? We have the weight acting down, and you have the normal acting up. That force of kinetic friction is the coefficient of kinetic friction multiplied by the normal force, and the normal force for a flat surface is simply equal to mg. So how do you now calculate the work done by that force? Well, it's the magnitude of the force. It's the magnitude of the displacement. So think about what the displacement is here. It's this whole distance, right? It's L plus D is that total displacement. So here I do L plus D. And then cosine of the angle between that displacement and the force of friction. Well, that's 180 for this case. So again, that is going to introduce a factor of -1 here, because cos of 180 is -1. All right, what else we have? Now we have the work done by the spring. This is also a conservative force. So again, the work done by the spring now is going to be U initial minus U final. For the spring, U initial is 0, okay? So we don't have anything to worry about. So we have 0 for U initial. What's U final? U final is how much spring potential energy is stored over here. So that final spring potential energy is 1/2 K and D squared in this case. And you sum those three terms, you have to get 0. We notice here that this here is also going to be a negative value. It's negative because the spring force acts to the left and the displacement is to the right. Therefore, you have opposite vectors over here. So that always means you're going to have negative work being done by that force. So if we think about this expression now, what do we want to solve for? We want to solve for what h is. So we have to do a little bit more algebra here. So what I'm going to do is just get h by itself. So I have to bring those other two terms on the other side. And then I have to divide through by little mg. All right, so if I bring those terms on the other side here, I'm going to get, well, let me just write this one, kd squared, and divided by mg. What else? Plus, here I'm going to get mu k. The mg is going to cancel out. And here I'm left with L plus D multiplied by that coefficient of kinetic friction. All right, now we can substitute in all the values here. Actually, let me just go down below just to give me a little bit more space. That spring constant is 45. That distance D was 0.15, and you square that one. My mass was 4, and little g was 9.8. plus the coefficient of kinetic friction, 0.2. The L is 0.4, and that distance, again, 0.15. All right, I put everything in the calculator. This is a pretty lengthy problem here. I get a value of 0.123 meters. Let me box that up. That corresponds to approximately choice A is the best choice for this one. All right, question 21 says, what is the work done by the spring as it stops the block? All right, well, we just talked about that. The work done by the spring, again, the spring force is a conservative force. So the work done by the spring you can write as minus the change of potential energy, which is what? Minus U final minus U initial. All right, you distribute out that negative sign and you get U initial minus U final. Notice that U initial for the spring is 0. There is no initial compression of that spring. And then what do you have? You have minus 1/2 kd squared. All right, this we put is exactly the same term that appeared over here. Notice that we get a negative value. So you substitute my values in here. And again, I'm going to get a negative value, 0.506 joules is the work done by the spring. So that corresponds to choice B. Problem 22 says, now if a block with half the mass was released from the top, the distance that the spring compressed would be what? Larger than 0.075, equal or less than 0.075. All right, well, let's think about it. In the original part, I have that the distance compressed was 0.15. So you can see that these numbers correspond to half the distance. So what we need to see is what is the relationship between the distance and the mass of the block. In order to do that, we're going to use this equation right here, equation 1. And for now, to simplify it, I'm just going to neglect the friction term right here. So just imagine there was no friction. What would it look like in that case? So here you'd have mgh equals to 1/2, I bring that on the other side, kd squared. So the distance d that the spring compresses in the absence of friction would look like this. Mgh, and again divided by that spring constant k. So think about now the relationship. So if you half the mass, what happens to that distance? If I make the mass small, the distance d is going to be small, right? And in order for me to make this distance half of what it was previously, I would have to make the mass 4 times smaller. But in this case, I'm only making it half the value. All right, so if you make it half the value, what are you going to get? You're going to get a value that is going to be less than 0.075. All right, so I think C is the best answer for this problem. All right, here's problem 12. We have a skateboarder stands at the edge of a dry swimming pool. The pool's floor varies smoothly from the shallow to the deep end, as shown in the figure. The skateboarder's mass is 55 kg without a skateboard. The mass of the skateboard is 1.6. The pool's deepest point is located at a distance d, 3.4 meters below the pool's edge. Question 20 says, first, the skateboarder checks her skateboard by rolling it down by itself from below the shallow end's edge of the pool to find that the skateboard rises 0.2 meters below the deep end's edge before sliding back. All right, what was the work done by friction on the skateboard during the first passage of the pool? So it means that it gets right at about this point here, and it leaves a little bit of height here. It leaves 0.2 meters below that top edge right here. So how would you calculate this? Well, one easy way to do it is that the work done by friction, again, as you're rolling, you're losing energy. This guy here is typically a negative value. So I would answer this problem simply by answering choice A right here. Because we know we don't make it all the way back to the top because there was work done by friction. We've taken some of that energy away. Now, if you wanted to actually get to that number, one way you would do it is, I would say that I would compare this initial point all the way to this high point over here, because I know that the final speed over here is 0. The board only goes up to that height. So that means that the net work being done on that skateboard has to be 0. There's no change in kinetic energy of that skateboard. So what do we have? Well, there's forces at play here. There's work being done by gravity during that process. What else? There's also work being done by friction in that process, and those must sum to 0. So right away you bring the work done by gravity onto the other side, so you get that the work done by friction must be minus whatever work was done by gravity in that case. So how do you calculate the work done by gravity? The work done by gravity, the easiest way is to do negative the change of gravitational potential energy. Notice those two negative signs cancel out, and then you're going to be left with U final minus U initial. All right, so what do you get? Well, your final height here, I'm going to measure all the heights from the bottom of this pool, right? So what do we get? And again, we're only looking at the mass of the skateboard here because it was the skateboard only that went down that ramp. So we have just the mass of the skateboard, M. Y final is going to be 3.2 meters. Okay, I'll call this Y final, and then minus Y initial. So now we substitute in all our values. So here this is 1.6, mass of the skateboard, 9.8 for little g, and here we get 3.2 and minus 3.4. You put all those numbers, you're going to get the work done by friction. Notice it's going to be negative over here, so we get minus 3.14 joules when you substitute the numbers in the calculator. Not too bad. All right, problem 21 says, after adjusting the skateboard to run nearly frictionless, the skateboarder drops in on her skateboard from the shallow end of the pool. As she goes along the floor of the pool, she pumps the skateboard and then exits the pool at the deep end's edge. The same height as where she started, over here on the right-hand side. Vertically upward with a speed of 4 meters per second. How much work did the skateboarder do during the run? All right, in order to answer this one, I would say that the work should be the change of kinetic energy. All right, so if she started over here at rest, she has 0 kinetic energy, so that means it's K final minus K initial, where K initial is 0. K final now is simply the final kinetic energy. 1/2, again, it's the total mass here, so it'll be the mass of the skateboard plus the mass of the skateboarder. So in this case here, it's what, 55 plus 1.6, and then multiplied by her speed squared. To calculate that work, I got 453 joules. Let me go ahead and box that up, and that corresponds to choice C, I think is the best choice. Notice that she would have to do positive work. I'd get rid of anything negative right away. That there doesn't make much sense. All right, what's left? Question 22 says, how much air does she get? Here, air refers to that maximum distance. So how high is she going to go measured from here? This is what they refer to air, and I'm going to call that H above this deep end over here. Yeah, so assuming the skateboard remains intact with the skateboarder. So what we have here is we can use conservation of energy in order to solve this problem, right? What we're going to do is look at, over here we know she's moving here at a speed of 4 meters per second. And then at the top, we know that her speed is going to be 0 at the max height, right, at this final height. So what we're doing is we're converting all of this initial kinetic energy into gravitational potential energy. So this is how I would set it up, equals to K final plus U final. K final is going to be 0, right, at the max height. What else? U initial, I'm going to set that to 0, so I'm measuring my height here with respect to that deep end's edge. And now all you want to do is substitute our values. So what do we get? We're going to get that initial kinetic energy is 1/2. It's the total mass of everything. What else? V squared has to be equal to the final gravitational potential energy of everything. So that's M total. GH. See that the total masses cancel out. They're on both sides. And now all you want to do is solve for H. So you get H is equal to V squared divided by 2 times little g. We substitute our numbers. You get 4 squared divided by 2 times 9.8. And now we're going to get a final height of 0.815 meters. All right, and that there corresponds to choice C. That would be how much air that skateboarder got. All right, kind of a nice problem. Let's go to problem 13. Problem 13 says a box of mass 6 kilograms is being pulled by a string along a rough horizontal surface. The tension in the string remains constant throughout the process and has a magnitude T. The string makes an angle of 28 degrees with the surface. The box is initially at rest. After the box has moved 2.3 meters, the work done by the string is 50 joules, and the work done by friction is 41 joules. What is the magnitude of the tension Okay, well, in order to answer this one, I would probably, since we know the work done by the string, right, ST here is 50. Again, the value, or the way you calculated this would be that it'd be the magnitude of the force, the displacement, and again, cos of the angle between that force and that displacement, that corresponds to cos of theta over here. This one we know, right? So all we have to do now is just rearrange this equation to solve for tension. So you get the work done by the string here, or by the tension force, divided by that displacement and cos of that angle. And now we can substitute our values. So we get 50. Here we get the distance is 2.3 meters. And now cosine of 28 degrees. So we get a tension force here, which is 24.6 newtons. All right, that there corresponds to choice C. Go ahead and box that up. All right, not too bad a question. The next says, what is the speed of the block after it's moved this distance? Well, in order to find that, we're going to use the work energy theorem. It says that the net work, again, the only things that are doing work here are going to be that the string is doing work and also friction is doing work in this problem. That's it. So that must be equal to the change of kinetic energy, which is always a final value minus an initial value. The initial value is 0. The box starts from rest. And I'm looking for the speed. The speed is going to be inside this kinetic energy. So let's go ahead and just write out this final kinetic energy is 1/2 the mass of that block, v squared. All right, so how do we just rearrange this equation? So we get v is equal to 2 times the work done by the string plus the work done by the friction, divided by the mass m, and then you take the square root of everything. Now there is one important thing to consider over here. The friction force acts in this direction, right? That is, friction and tension acts like this. So when you substitute your numbers into this expression, you have to be careful. See if they got you. The work done by the string is a positive value of 50. The work done by friction is 41. Well, that's the magnitude of it. All right, it really should be a negative number in there, and then you divide by that mass. So my speed of the block after, substitute everything in, I get 1.73 meters per second. Let's go ahead and box that up. That corresponds to choice B. All right, next they say, what is the coefficient of kinetic friction between the box and the surface? Well, again, for that, they've told us that the work done by the friction, at least the magnitude of it, is equal to 41. So we know this value. If you go ahead and apply the equation, how would you calculate it? Well, you'd say it'd be the coefficient times the normal force. What is the normal force in this case? Well, the normal force, you actually have to calculate it over here. So we have to be careful of. So I'm going to come back to that one. So that's the force of friction. The displacement we know is 2.3 meters. And then, again, you're going to have cos of 180, but if I'm worried just about the magnitude, that is the magnitude of the work done by that force of friction. So in order to calculate the normal force now, what you have to do is you have to look at all the forces acting in that vertical component. Well, we have to break the tension down into a vertical component, and that vertical component is T sine of 28 degrees. So now how do we figure out the normal force? Well, you add up all of the forces here in that vertical direction, and this is what it looks like. We've got the normal force acting up, we've got the weight acting down, and we also have this component here of the tension, which is helping lift the block. So this is what it looks like. Plus T sine of that angle theta, and then minus the weight equals to 0. All right, I'm going to give myself a bit more space. So my normal force now is equal to the weight, mg, but you can't forget about this, T sine of that angle theta. All right, so that's what you have to do is you have to substitute that normal force into my work expression, and this will allow us to solve now for that coefficient of kinetic friction. So let me go ahead and just write down the expression. It's the work done by the friction force divided by that displacement, and then multiplied here by this normal force, which is mg minus T sine of the angle theta. All right, so substitute in all the numbers. All right, so this is what we get. We get 41 here for that work done by the friction. The distance was 2.3. Now you substitute everything here, 9.8, and then minus the tension we had, 24.6, and then sine of 28 degrees. Close that bracket. All right, at the end, you substitute all those numbers, and I got a value of 0.377 for my coefficient of kinetic friction. Not too bad. That corresponds to choice E. All right, question 7 now says, if the experiment is repeated, but with this time pulling on the string with twice the force, the kinetic energy of the box after being pulled at 2.3 meters would be less than twice the kinetic energy of the original case, twice the kinetic energy, or more than twice. Okay, so for this one, what we're going to do here is I'm going to have to give myself a little bit of space. So I'm going to remove some of this previous work over here just so we can talk about this. So we have to compare what is the kinetic energy in case number 1 to case number 2. So where is the kinetic energy for case number 1? Well, it's right here, right? In this equation over here. Good. So we see that that final kinetic energy, Kf, is equal to what? It's the work done by the string. What else? Plus the work done by the friction. Okay. Well, the work done by the string is T delta x, cosine of that angle. And what about the work done by the friction? The work done by the friction is the force of friction, mu k, multiplied by the normal, which is what? mg minus t sine of theta. And what else? Times that displacement. Okay. And now times cos of 180. So that just introduces a negative sign here in the front. Just go ahead and do that. All right, and this is the final kinetic energy. So now what happens now if I double the tension? Well, I get 2t over here, and I'm going to get 2t over here. So again, but look at this term right here. There is no factor of 2 that gets introduced over here. So although you've doubled the work done by the tension, you've doubled the work done over here for this term, you haven't doubled this term over here. So at the end of the day, you're going to get less than twice the kinetic energy if you apply twice the tension, because there's no multiplicative factor of 2 that appears in all the terms. Problem 14 says a block of mass m 1.5 kilograms is released from rest from a height of 1.5 meters on a frictionless inclined plane that makes an angle of 35 degrees with respect to the horizontal. At the bottom of the incline, it encounters a frictionless horizontal surface that has a length of 2.5 meters. After sliding across the horizontal surface, the mass goes up a second incline that makes also an angle of 35 degrees with respect to the horizontal, except this second incline here has a kinetic coefficient of friction of mu k, 0.45. It also has a static coefficient of 0.52. All right, first question says, what is the maximum height, h max here, that the block reaches on the right ramp? All right, this is a calculation, and probably the best way to start, I think, would be to use the work-energy theorem. The work done by all of the forces must be equal to the change of kinetic energy of the block. It starts over here with an initial velocity of equals to 0. Once it reaches its final height, it also has a final speed equals to 0. So that's it. So what is doing work? Well, there is work done by gravity here on the left block, right? When it's sliding down that left ramp, rather. What else? There is work done by gravity when it's going up that ramp. So I'm going to call that the gravity done on the right ramp over here. And now there's also friction over here. So plus the whatever work done by friction as it's sliding up that ramp. When I add those three terms, they must be equal to 0. All right, the work done by gravity on this left ramp, again, the work done by gravity, if it's a conservative force, we've done this many times now, so the work done by gravity I can write as minus the change of gravitational potential energy. It's Ui minus Uf. So what is Ui? Well, that is mghi. That's easy. And what about on the right-hand ramp? Well, the right ramp, you're going from someplace low toward a high place. So for that right ramp, the initial is 0, so this term is actually negative, and it's mgh max. Okay, so that's it for that term. What about the work done by friction now? Well, think about that block as it is sliding up. You have a weight acting down. We have a normal force acting perpendicular to the ramp. And here I've got kinetic friction, which is in this direction. Now the force of kinetic friction is always a coefficient of kinetic friction multiplied by a normal force. The normal force for a block on a slope is that perpendicular component of the weight, mg cos theta. All right, so that allows us to do this. So we get work done by friction is the force, is this, mg cosine of theta. What else? The distance that it's going to slide a certain distance over here. I'm going to call it delta x. And now multiplied by cos of the angle between the friction and the distance, or the displacement rather. The displacement is this way. That's the delta x. That angle between the force and that displacement is 180. So you need that in that definition. That'll introduce that -1 sign that we're looking for the work done by the kinetic friction, right? Oops, that's not what I wanted to write. I just want to write -1 here. All right, so now that when you sum those three terms, you must get 0. So all we have to do now is, we have to do a bit of algebra. We have to rearrange this term here to find what is this maximum height. Okay, so what we can do is divide through by mg. You see all the terms have mg, so that kind of simplifies your life a little bit, mg. The other thing I have to worry about is what is this delta x? So for that, let's think about this ramp. Delta x is the distance that I slide on that ramp. That is delta x. This here is the angle theta of the ramp. That's 35 degrees. Again, that distance that I'm going to slide up the ramp is going to be related to this maximum height right here, right? If you use, for example, sine of 35 degrees, I know that is h max divided by delta x. So delta x is h max over sine of 35 degrees. So let's go ahead now and just get rid of that delta x. Get rid of this. I can get rid of this cos of 180 as long as I introduce a negative sign over here. And this is delta x, which is h max divided by sine of 35, or I could just call it the angle theta. All right, the goal again is to isolate h max. It appears in both terms. If you bring them to the other side, you can then isolate h max. I'm just going to go ahead and bring that h max terms to the other side. I factor out h max and I'm left with this, 1 plus mu k. Again, that gets divided now by tangent of theta because you have sine over cos. Sine is in the denominator. And that there is, you have h initial here on this side. All right, so my final expression here before I substitute the numbers, this problem is a little bit complicated, right? You have to be careful. Mu k divided by tangent of theta. All right, we substitute the values now, 1.5. 1 plus the coefficient of kinetic friction was 0.45. And again, that angle of the ramp was 35 degrees. All right, I substitute the values and I got 0.913 meters. Again, you'd expect to get an answer that is a little bit less than where you started. Again, it depends on how much friction there is and what is the angle of the ramp. H max corresponds to choice A right here. All right, question 14 now says, after reaching H max, what does the block do? Does it slide all the way down the ramp and back across the frictionless surface? Does it stop and remain in that position? Or does it slide partway down and then come to a stop? All right, so in order to answer this, what you have to do is you have to look at the forces once you're on this side of the ramp. Okay, so let's go ahead and do that once we're actually stopped. All right, so I'm going to do a free body diagram here on this block. Let's go ahead and do that. And in order to do this, let me give myself some more space to work with. Okay, let's redraw the block and draw a free body diagram. So what do we have? You have mg acting down. We have the normal force acting up. All right. Again, that component, the weight I can break down. Break it down into a perpendicular component and into a parallel component. This component is mg sine of theta, the angle of the ramp. This component is mg cosine of theta. Well, choice B says, will it remain at that position right here? Well, what do we have to do? In order to do that, you have to compare it to the static friction. What is the maximum force of static friction that you're going to get here? that maximum force of static friction you can write as the coefficient of static friction multiplied by that normal force, which is mg cosine of theta. Now what we have to do is you have to compare those magnitudes, and you have to compare it to the weight parallel to the ramp, which is mg sine of theta. So which angle is going to be, or which of these forces is going to be bigger? All right, so I've gone through and I've substituted the numbers here for the mass little g and sine of theta, and for that component of the weight here I got 8.43 newtons. That is what is pulling down on that block to go down the ramp. What is trying to prevent it from going there is this force of static friction, and the maximum value that it could be, again, I've substituted those numbers in and I got 6.26 newtons. So what this tells us here is that this force here is going to be bigger than the static friction. So that means it's going to accelerate down the ramp, okay? And once it starts to move, we know that the force of static friction or the force of kinetic friction is going to be smaller, right, than the static friction, because that coefficient is smaller. So it's just going to slide all the way down the ramp and then back across that horizontal surface. All right, kind of a little bit of a tricky problem involving kinetic and static friction. All right, here's problem 15. It says a block of mass 2.8 kg starts from rest and is pulled across a rough floor by a horizontal rope. There is friction between the box and the floor with kinetic coefficient of friction mu k. The tension in the rope is 22 newtons. After moving a distance of 2 meters, the box has a velocity of 3.9 meters per second. What is the work done by the rope as the block is moved 2 meters? All right, so the easiest way to solve this one is just to apply our formula. The work done by the rope, or by the tension force in this case, is the magnitude of that force, the magnitude of the displacement, cos of the angle between both of those. In this case, it's cos of 0 degrees. So that's simply equal to 1. So this is super straightforward. The tension force is 22 newtons. We pull it a distance of 2 meters, so that gives us 44 joules of work, and that corresponds to choice B. All right, question 18 says, what is mu k, the coefficient of kinetic friction between the block and the floor? Now for this one, I'm going to use the work energy theorem. It says that the net work is equal to the change of kinetic energy of the block, and this is K final minus K initial. Well, guess what? The block starts from rest, so get rid of that term right away. We're done. The K final is 1/2 mv squared, and my final velocity is that 3.9 meters per second. So let's think about our free body diagram. We've got the weight acting down, that has a value mg. We also have a normal force acting up. And in addition to that, now we also have kinetic friction. Kinetic friction is acting in this direction. All right, so when you think about the net work, you have to add up all of the contributions. So we get the work done by the rope, or by the tension force, plus the work done by the force of friction, and then that's it. The normal and the weight don't do any work in this case, and that has to be equal to 1/2 mv squared. Now the way we're going to get the coefficient of kinetic friction is, well, the work done by friction will depend on the force of friction. So that's how we're going to introduce that term. The work done by the rope, we already know that value, so you can bring that to the other side. And let's write down our expression now for the work done by this force of kinetic friction. So this guy right here becomes mu k multiplied by the normal, which is nothing more than mg, and then multiplied by cos of, let's just put in that displacement first, right? It slides a certain distance, which is delta x, which we're told is 2 meters in this case. And now multiplied by cos of 180. That's the angle between that force of friction. And again, that displacement is this way. That's my delta x. So that'll introduce, again, a factor of -1 over here. All right, now let's bring everything else on the other side. So what we get is 1/2 mv squared, and we get minus the work done by the rope or by the tension. Okay, so that's it. All you have to do now is just isolate what this value of mu k is. So you get mu k. Again, just divide through by all of these terms. So you get 1/2 mv squared minus the work done by the rope. divided by, now this is going to be minus mg multiplied by delta x. This minus sign might bug you, but don't worry about it. It's going to work out, and we're going to have to get a positive number for the coefficient. So we substitute our numbers here. We get 2.8 for the mass. We get my final speed is 3.9 squared minus that 44. And now divided by minus 2.8. Again, little g is 9.8 and multiplied by that distance here, which is 2. All right, substitute the numbers in the calculator, and I got a coefficient of kinetic friction, which was equal to 0.41. So that there corresponds to choice D. All right, let me just box that up. All right, that's kind of a nice little problem here. Pretty straightforward application of the work energy theorem. Let's go to our last problem now. All right, here's problem 16. It says a spring with spring constant K equals to 250 newtons per meter is fixed to a frictionless inclined plane that makes an angle of 28 degrees with the horizontal. The relaxed length of the spring is L0 as shown in the left figure over here. A block of mass 2.8 kilograms is attached to that spring. The new equilibrium length is 0.4 meters. Again, that's measured from the end as shown in that middle image. How far does the spring stretch when the block is attached? All right, so we're looking for that distance L1 minus L0. So for that, I would recommend doing a free body diagram of the block in this middle picture right here. So what do we have? We've got the weight acting down. We've also got a normal force, which is in this direction. And now there is one additional force, is this spring force. The spring force, I'll call it Fs. And the magnitude of that spring force is K multiplied by X. And X is how much it's stretched, right? This is the distance that it's stretched from the equilibrium. So actually what I would do is I would write this X value here as being 1. I'd write it as a magnitude of being L1 minus L0. That is really what this stretching amount is. All right, so this object is in equilibrium. The next thing you could do is you could break the weight down into two components. So you have a weight perpendicular, right here. This component of that force is mg cosine of theta. Theta is the angle of the ramp. It's also that angle in this right here. And that means there's also a parallel component of the weight. This is mg sine of theta. All right, so what do we want to do? Well, you want this object to be in equilibrium. So that means if you add up all the forces, they have to be equal to 0. So let's add up all the forces, for example, in the x direction. And let me call this the positive x direction. So what do we have? That means we have K, L1 minus L0, and then minus mg sine of theta acting down the ramp has to be equal to 0. The magnitudes of both of those forces must be the same. So we get an expression now, L1 minus L0, which is what we're trying to solve for. Has to be equal to mg sine of theta and divided by that spring constant K. So now you can substitute everything in here. We get 2.8 for that mass, 9.8 for little g, sine of 28 degrees, and divided by that spring constant. This is in the right units, 250 newtons per meter. All right, we substitute in everything here, and I get a value of 0.0516 meters. All right, that there corresponds to, looks like choice B is the best answer for that choice. All right, question 20 says, the block is then pulled down the ramp, further stretching that spring to a length L2 here of 0.48 meters as illustrated in the right image and released. As the block slides up and down the ramp, at what spring length will it be moving the fastest? All right, when is it going to be moving the fastest, you think? Well, again, this is going to be moving the fastest once it's in this equilibrium position right here, okay? That is when you are going to convert all of that spring potential energy that you have down here at the bottom. You're going to be converting that into into kinetic energy as it goes through this equilibrium. All right, problem 21 says, what is the speed of the block when the spring length is this, 0.35 meters? All right, I'm going to take this to be my initial position over here. This is not moving. At this position, all my energy is spring potential energy. Again, when you choose this position here, this middle position to be the new equilibrium position, the way that you solve these problems now is you don't have to worry about including the effects due to gravitational potential energy. All right, they're kind of already included over here when you set up this new equilibrium position. So the only thing we need to worry about is kinetic and spring potential energy. So at any other point now, when the spring is any other length, that means we're going to split up our energy. Some of it is going to be kinetic energy, and some of it is still spring potential energy. So when x is when the spring length is 0.35, guess what? That means that the x value, again, imagine where 0.35 is. That L1 length is 0.4. So 0.35 means my x value is 0.05 meters, right? It's the distance from the equilibrium position that we care about. It's not the spring length that goes inside this elastic potential energy of the spring. So my goal now is simply to solve for what is the speed. So you have to isolate the speed. The first thing you can cancel are all the 1/2s that appear in all the terms. Next thing is we're going to bring this mx squared on the other side and divide through by the mass. Actually, let's just divide through by the mass right now. Gets rid of those, and it will introduce a mass term right here. So the next thing I have is that v is going to be equal to the square root of k over m. And this here is a squared minus x squared. All right, so now you can substitute in all the values. My spring constant is 250. My mass was 2.8 kg. And now that amplitude, the amplitude of the motion, you have to remember what that is. The amplitude now is not the length of the spring. The amplitude for my problem is actually L2 minus L1. That's the maximum amount of stretching that you're going to have. So in this case, this is 0.08. All right, so here that means I put 0.08 squared over here, and then minus 0.05 squared for that spring position. All right, you substitute in all our numbers now, and we get a speed of roughly 0.59 meters per second. All right, that corresponds here to choice A as being the best choice. Let me go ahead and box that up. All right, folks, that there concludes this really long problem set, 16 problems. It's the biggest video I've ever done. Hopefully you've learned a lot about applying work energy, potential energy, kinetic energy. You enjoyed this video. All right, good luck on your exams, folks. We'll see you next time.